So, hello everybody. Today we welcome Tommaso Pacini from University of Torino as our speaker. He shall speak on a day of two geometries, G2 versus Kähler. Please.
Thank you. Thank you, Van and other organizers for letting me give this talk. And I think I will try to keep this very informal. And so please interrupt with comments and questions as we go ahead. I should also try to be non-technical, but we can discuss technicalities if you wish. So yes, the topic is a comparison between two different types of geometry, G2 geometry and Kähler geometry. And of course, Kähler is an extremely classical geometry, very well known. There is a vast amount of results in this direction. G2 geometry is instead much more recent, and perhaps the main impulse in this direction only started perhaps 20 years ago. So we can consider it a new exotic type of geometry, which is similar. It has some analogies with Kähler geometry from various points of view. First of all, because both are of interest to physicists who work in string theory and to people who work in the direction of mirror symmetry. So the idea of the seminar is to try to discuss the analogies between them and use the wisdom we have accumulated in Kähler geometry across centuries to understand which are the best directions to continue developing G2 geometry. And so to be specific, I will make a choice of certain topics: submanifold geometry and function theory. I will discuss these as we go along. And in particular, I will try to show how they interact and where the boundary is of research at this moment to understand perhaps new directions in which we can develop these topics. Okay, so I enjoy summarizing this this clash between different geometries in the following way. It turns out Hollywood was already prepared for discussing the G versus K exotic and classical geometries. So, okay, to begin, I will give a very brief outline of the main ingredients we shall use in Kähler geometry. I expect most of you already know the definitions, so it is not necessary to emphasize the definitions. And in the same way, I will not be very formal in defining G2 geometry, G2 manifolds, but hopefully the summary that I shall give you will help give some understanding of the ingredients in the analogies. So a Kähler manifold is something that can happen in many different dimensions. It is equipped with a complex structure, which says that the manifold is modeled on Cn. And then you can use some linear algebra to provide further structures, such as an orientation. The second initial ingredient, is a symplectic form, a two form, which we will use to obtain an isomorphism between the tangent and the cotangent bundle. So now to develop the theory, we need these structures to be compatible, and the compatibility will generate a metric. So Kähler geometry is also Riemannian geometry. And then we need to add some extra analytic conditions. We want J to generate holomorphic coordinates, and we want the symplectic form to be closed. I will explain why as we go along. And so out of this, what we get is an extremely rich geometry, both from the point of view of submanifolds, because we have, for example, several different categories of submanifolds to play with. Complex and Lagrangian, you should think of as two opposite categories, two extreme opposite types of submanifolds inside a Kähler manifold. There's also a very rich function theory, because we can talk both about holomorphic functions and also about plurisubharmonic functions. We will come back to this later on. And then there are some additional ingredients, such as a notion of positivity, which, for example, we can define using differential forms, but then it has a geometric meaning in terms of line bundles and curvature. So this is the basic structure of Kähler manifolds, and we shall use it as the comparison for G2 manifolds. Now, a G2 manifold is something that very rigidly lives only in dimension 7. So it is a completely real geometry. It is not complex in any way. It only has one algebraic structure to begin with, and this is a cross product, which means that the manifold is modeled on the imaginary part of the octonions with their multiplication. And I'll just say we restrict to the imaginary part of the octonions because the real part of the octonions is a trivial component. It is one extra dimension. It is an extra R, which is not particularly interesting to add on. All the action happens in the 7 imaginary directions. So again, we can use linear algebra to generate an orientation, but in this particular situation, linear algebra turns out to be much more powerful, and by itself, it also generates a metric and a differential form, so that this particular identity is satisfied. So this is what we compare to the algebraic ingredients of Kähler geometry. Then we add on the analytic conditions, the same analytic condition, we want the form to be closed. And what we get out of this, once again, is a very rich geometry of submanifolds. There are 2 classes of submanifolds which are extremal in a way that I shall discuss. These are the associative and the co-associative submanifolds. It turns out, and this is a very recent discovery from 15, 20 years ago by Harvey and Lawson, that there is also a very interesting function theory associated to G2 manifolds. These are again called plurisubharmonic functions, and the theory is analogous. It is almost identical to, from an analytic perspective, to what you find in the Kähler world. And then in some sense, the current boundary of our knowledge stops here. There, G2 geometry has not been developed very much beyond these initial ingredients. So let's see. what I now want to do is to emphasize the analogies between G2 and Kähler from a very basic perspective. Again, please ask me if you have questions. Now I shall be a little bit more specific in my definitions. So we can start comparing the differential forms, the Kähler form and the G2 form. And they satisfy a same normalization condition, which we can use to define the categories of submanifolds we are interested in. In the Kähler side, we can maximize omega up to the value 1, so that omega is equal to the volume form of a submanifold. And the submanifolds that satisfy this condition are the complex curves, more generally, the complex submanifolds. Or we can try to minimize omega and take it all the way down to the other side, where omega is equal to 0. These define the Lagrangian submanifolds. And exactly the same thing we can do in the G2 case. We can maximize phi and define associative submanifolds, or we can minimize it and define co-associative. And all of these submanifolds can equivalently be defined also using the other algebraic structure, so that, for example, complex curves and associative submanifolds are closed with respect to the algebraic structure, while instead Lagrangian and co-associative are such that when you apply the algebraic structure, you obtain normal vector fields, not tangent vector fields. So this is our dictionary in which J and cross product are the internal operations, omega and phi are the differential forms, and the submanifolds are somehow twinned as complex with associative and Lagrangian and co-associative. So this is the dictionary we shall work with. And what I will do is I will develop this dictionary as we go along. So let's see what the analytic conditions give us with these ingredients. The fact that the forms are closed is necessary to obtain local existence results for the submanifolds to make sure that Lagrangians and co-associatives exist, but also they provide a very nice moduli spaces in both cases. Lagrangians have smooth infinite dimensional moduli spaces. Co-associatives have smooth finite dimensional moduli spaces. Now the function theory, let me give you a brief presentation of that. I was already saying in the Kähler case, we can talk about holomorphic functions defined by the operator d bar. But classically, we can also talk about plurisubharmonic functions defined by the operator d bar. Now, we shall prefer a different equivalent point of view for plurisubharmonic, which is closer to Riemannian geometry. You can take the function, calculates its Hessian using the metric, and it will be plurisubharmonic if its partial trace is positive. Partial trace, I mean the trace with respect to the Grassmannian or the submanifolds that we are interested in. These will be the complex lines in the Kähler case. And as I was saying, it is an interesting fact that exactly the same type of theory exists in many other geometries, in particular in many calibrated geometries. These are again called plurisubharmonic functions. And again, you can define them with an operator, or you can define them using the Hessian and asking for a certain partial non-negativity. And this,
Tommaso, would you remind the definition of the d-varphi?
Yes. So the analytic definition of plurisubharmonic in the G2 case is the following. You take the 3 form and you plug in the gradient of f. Then you get a 2 form. And so you differentiate that. And so you take d phi of f, and that is a 3 form again. And you want that to be positive in the sense that it gives positive values on oriented associative 3 planes. This is exactly the same definition as in the Kähler case, that dc of f you can calculate in the same way using omega.
Yes, thanks. Yeah.
But yes, I was saying I like the other point of view, the Hessian point of view, because it contains interesting intuition on plurisubharmonic functions. Remember that standard convexity means that the full Hessian has to be positive. And so these pseudo-convexity means that some sort of analog holes in the complex case or in the quaternionic case. That's really what these definitions are telling us. Okay, so I said we are mostly interested in how these function theory and geometry interact. So first, let me just remind you that the function theory in the Kähler case also interacts. Holomorphic functions generate plurisubharmonic functions by taking the modulus. But these plurisubharmonic functions also interact with submanifolds, and in particular, they offer some obstructions to the existence of submanifolds. So if you have special types of plurisubharmonic functions in a certain region of your manifold, then you know that in that region, there cannot exist certain types of submanifolds. For example, there are no compact complex submanifolds in Cn, because on Cn, you can find this plurisubharmonic function given by the norm, the square of the norms of this f here. And the same thing happens again in G2, because as I said, from an analytic perspective, everything that's true in the in one of these pluripotential theories also typically works in the others. Now, what I want to do.
Your result.
Go ahead.
Is it the second concerning G2 that your result? The abstraction of the existence of compact associated submanifolds that you find the example. Did you prove this reason and find the example?
Oh, that's a good point. No, I don't know of particularly interesting examples. I mean, certainly in R7. So we can have the analogous example as in Cn. We can repeat in R7, where I think I'm not sure. I think again there the distance squared will give you a plurisubharmonic function. Yes, because it gives you a convex function, and so it's also plurisubharmonic. But we did not really need that to know that in R7 there do not exist compact associative submanifolds. Again,
yeah.
But that's an important point, Van, because what Harvey Lawson have given us is what seems to be a very powerful tool, but it has not been applied in geometry yet, and it has not been studied very much in examples.
Yeah, but basically, the first example is how to say very easy without any pseudo how to say subharmonic function, right? There are many proof of the non-existence of compact complex because calibrated geometry may be simpler.
That's right. That's right. Even the statement in Cn can be proved in simpler ways. Absolutely. Yeah. But of course, in Cn, that example generalizes to all Stein manifolds. And so it generates the notion of a Stein manifold, and so there's a lot of extra geometry there. Equivalently, you can define a Stein G2 manifold, but nothing has been done yet, as far as I know, to study their geometry.
Yes, thanks. Yeah.
Perfect. Okay, so again, we want to see where these analogies, how far they go, and how far the interactions go, and where instead they stop based on our current knowledge. So let me discuss the first problem I mentioned, the volume functionals for submanifolds. Now, this is a very general topic which you can discuss in any Riemannian context. You can take a submanifold and define its volume form. Then you can integrate the volume form and obtain the volume, the value of its volume, the volume functional. And if you do that with respect to families of submanifolds, then it becomes interesting to see which submanifolds are special because they are critical points of volume, and which are very special because they are minimum points for the volume. And so this involves taking first and second derivatives of the volume functional. And that's what the first variation, the variation formula do for us, again, in a very general Riemannian situation. The first variation formula shows the importance of mean curvature inside this, to study this problem. The second variation is a little bit more complicated to work with because you start by taking the derivative of the first variation, and what you get is lots of little pieces which do not have independent geometric interest. And so what you have to do is take those pieces and put them together in a smart way to create larger pieces that do have geometric meaning. And so the final formula that you get, you see on this page, contains, for example, the Riemannian curvature of the submanifold. And so the formula now shows that you can control the stability of a submanifold using the curvature of the ambient space. Now, what we would like to do is see how these formula can be applied in the more special case of Kähler manifolds and G2 manifolds. And it turns out that something interesting happens. If you look at complex or associative submanifolds, it turns out that there is a different point of view on these submanifolds called calibrated geometry, which says that these submanifolds are always minimal. And so H is 0, so the first variation gives the value 0. But actually, they are also always minimum points. And so the second variation is always non-negative. And in both cases, you see that it is not necessary to actually use the formula. You already know what the answer will be. Now, instead, in the Lagrangian and co-associative case, something different happens. These, in the context that I'm talking about, are not calibrated, but and so we do not have any information on them. But the formula we are trying to use do not use the extra Kähler or G2 geometry, and so they cannot tell us anything specific about these submanifolds. So this problem was studied already in the past by O and also by Van, who realized that in Kähler geometry, if you're looking at Lagrangian submanifolds, you can take the second variation formula and all those little pieces I was talking about And you can actually combine them in a different way using the symmetries of the Kähler geometry, of the Kähler curvature. The first piece is a Laplacian, and it provides a positive contribution. And so that goes in the direction of stability. And the second piece is better than the previous term I showed you, because this is Ricci tensor rather than general Riemannian tensor. And so this new formula shows that you can control stability only using the Ricci curvature of the manifold, of the Kähler manifold, not the full curvature tensor. So my question was whether there exists an analog of this type of formula in G2 geometry. So to discuss this, I'm going to slightly change our point of view and not talk about the 3 form, but I shall talk about the dual 4 form, the Hodge dual. It is an equivalent tensor, but it is useful because we can use it to study the covariant derivatives of the G2 structure phi. And it shows the importance of a certain torsion tensor in G2 geometry. And then it is also interesting because we are interested in co-associative submanifolds. I defined co-associative submanifolds saying that the 3 form is equal to 0. But equivalently, we can define them as those on which the 4 form is equal to 1. And when you say that a differential form is equal to 1, you are really saying that the form is equal to the volume form. And so what you are saying is that the local data of the submanifold, of the volume form on the submanifold, extends to the whole manifold and becomes a well-defined tensor psi on the whole manifold. And so it is interesting to see how much of the extrinsic geometry or intrinsic geometry of the submanifold has a global extension. And for example, at some point a few years ago with Jason Lotay, we showed that the mean curvature vector field is an expression of the torsion tensor, the G2 torsion tensor that I was talking about. But I was saying I'm really interested in the variation formula and specifically in the second variation. And now it seems I did some calculations. I'm not able to find a complete analog of O and Van's formula in the Kähler case, but something interesting happens. And this concerns the moduli spaces I was talking about. You take a co-associative submanifold, and geometrically it is very natural to deform it in the directions that keep it co-associative. You deform it inside the moduli space. And when you do that, it turns out that the second variation formula once again has a shape which is very similar to the Kähler situation. You have, you see in this integral, there is a first term which concerns the global geometry of the torsion tensor, and a second term which once again, and this is, I think, is a little miracle of G2 geometry, it produces exactly the Ricci tensor again. And so once again, you can control stability using Ricci tensor instead of using the full Riemannian curvature. Problems of this type, again, I'm happy to mention, were again studied by Van under different assumptions of the G2 structure. I think it was in the calibrated case for co-associative manifolds.
So let me make a little comment here.
Yes.
Oh, okay. So you mentioned that I did something related to O, but actually that's my formula did not require that the Wafi is closed. In Kähler case, it's closed. Yeah, I work for the general head mission, but then the Ricci term in that case is a churn form.
Okay. Okay.
Yeah. So then,
course,
somehow that's a did it in Kähler case. Then I only remember because that's very long time ago. Then churn form translated Ricci and something like that. But he used a different method. But the formula how it's related. Yeah.
Excellent. Okay.
Okay.
Okay. Thank you. Yes. All right. So what we see here is that if we interpret the geometry in the right way, the analogy between G2 and Kähler continues also in this direction. So now I want to investigate the analogies in function theory. And after that, I will come back and show how these two different problems interact. I already mentioned that function theory is relevant to studying immersions. Now what I want to discuss is the relevance to a dual geometric problem of submersions. And so what I would like to do is compare classes of functions on the manifold and on the parameter space of submersion for that manifold, and see how a plurisubharmonic function on M, for example, transforms if I push it down to B, or conversely. And the reason I'm interested in this is because submersions are relevant to studying fibrations, and Lagrangian co-associative fibrations are an important ingredient in Kähler and G2 geometry. So let me first of all comment that this type of problem is again rather old. It goes back to the early 1900s with Hadamard and Hardy, who looked at functions defined in one complex variable on C star, in polar coordinates r and theta. They noticed that if the function is invariant with respect to theta, with respect to rotations, then the notion of subharmonic is equivalent to being convex in the function, in the variable r. In the more general case in which the function depends on both variables, then you can generate functions which depend only on one variable by integration or by taking the supremum across the circles. And the initial function, if the initial function is subharmonic, then the function you have generated this way will become convex. So in 1980, LaSalle realized that C star is the complexification of S1, and that the same game can be played for any group complexification. If you take a compact Lie group G, you can complexify it and talk about plurisubharmonic functions. You can quotient it by G to obtain a parameter space. And on that parameter space, there is some extra geometry, which you can use to talk about convex functions. And so he showed that the same relationships in terms of integrating functions or taking the supremum of functions occur in this very general context. So I would like to show that LaSalle's statement, which is a very analytic statement about function theory, actually is very relevant to geometry, and it can be expressed in very geometric terms. And I will do that by showing you this theorem, which is completely geometric. There's not very much function theory inside of it. We will take a Kähler manifold, which is toric. That means it has a certain group action. And the group will define some fibers. And we will calculate the volume of those fibers. And it turns out that the analytic properties of this volume functional are closely related to the curvature, the geometric curvature of the manifold. So the curvature is positive, the Ricci curvature is positive or negative, according to whether this function is concave or convex. And this is interesting because convexity is an extremely strong property. In particular, it implies uniqueness of of critical points. So previously, I was talking about stability. Stability is weaker. It tells you something local. Convexity tells you something global. It is a global uniqueness result. And when you read this theorem, you should realize it is a very wide, broad generalization of something which is obvious on the sphere. The sphere has positive curvature. And if you look at the group action by rotations, you will find only one orbit which is critical. It is the biggest orbit, the equator. All the other orbits will be the curves parallel to the equator, and those have smaller length, and the length goes down to 0 in a concave way. So every toric manifold, I'm claiming, works in the same way. So I will show you why this statement is basically the same as Lassalle's. We shall think of M as being the closure, the compactification of a complexified Lie group, which is C star to the n. And we shall look at the space of the orbits. The parameter space, if you want, can be viewed as the image of the moment map. And we shall now use this notion of positivity for Kähler manifolds. Specifically, we can take a line bundle, and the geometric positivity of its curvature can be related to functional positivity, because you can generate a potential function for the curvature form by measuring the length of a holomorphic section. And then the curvature will be positive if and only if the potential function is plurisubharmonic. So in Kähler geometry, what we will do is we will use the anti-canonical line bundle so that the Ricci curvature, so that the curvature of the line bundle is the Ricci curvature of the manifold. And the holomorphic section will be generated by the group action. So if you do the calculation, the length of that section is simply the density of the volume form along the orbits of the group action. And Lassalle is telling us we should integrate this to find a convex function. When we integrate it, we are finding exactly the volume or the logarithm of the volume of those orbits. So again, my statement is simply the geometric analog of Lassalle's analysis. Of course, Lassalle's analysis applies also to non-abelian group complexifications. And in fact, we can find similar theorems for other types of group compactifications. But you see, at the beginning of my seminar, I was comparing G2 and Kähler in terms of a battle between Godzilla and King Kong. Well, what we're doing here is the Kähler side, the Kong side of the story. So now we would like to understand better the G2 side. And we find an immediate problem, which is that LaSalle expresses his results in terms of complexifications, which make no sense in the G2 world. And so we need to find a different framework to study these relationships between function theories. And an interesting framework is given by Riemannian submersions, because a Riemannian submersion will take a metric on the manifold we are studying, and it will push it down to the parameter space. And when we have a metric on the parameter space, we can talk about convex functions or subharmonic functions on the parameter space. And we can compare that to the Harvey-Lawson pluri-subharmonic functions on the G2 manifold. So first, I need to show you that this framework does produce some results. And these are basically the same results that one can find in the Kähler case, one can also find in the G2 case. For example, Hadamard and Hardy said, look at invariant functions for the fibration. If we do that, we once again find a correspondence between pluri-subharmonic functions above and convex functions below in both geometries. Or we find a correspondence between pluri-subharmonic and subharmonic, depending on the assumptions that we put on our fibration. And LaSalle, Hardy, Hadamard also said that you should look at the more general case of functions which depend on all variables that are not invariant with respect to the submersion. When we do that, then we should integrate the function along the fibers. We are interested in convexity, and so we have to take second derivatives. And this is where we need the variation formula that I was talking about before, because you're taking second derivatives of an integral over a Lagrangian or a co-associative submanifold. And so you need to know how the volume form itself changes. So this is the way in which these two problems that I'm talking about interact on a different level. Now, if we use these statements and go again back to the Kähler situation, we will again find a nice geometric interpretation of the function theory. And what we find is a very strong relationship between the function theory below on the parameter space, for example, the Hessian, and the geometry above, for example, the Ricci curvature. Or you can think of this as a relationship between the Laplacian below and the scalar curvature above. So we can transform geometry into function theory according to these formula. Now, this is, however, so of course, what I would like to do now is say what happens in the G2 case. But you see, again, this is the boundary of our current knowledge. So let me just finish the seminar with a few extra comments. First of all, throughout the seminar, I've compared Ricci, curvature, and volume. And it is important to realize that this is a very classical problem. More generally, the problem is to provide a geometric interpretation to the various types of curvature that people use in Riemannian geometry. And it turns out that Ricci curvature is classically relatable to the volume. What we found, the new elements that we find in the Kähler case is a very strong relationship, because it is a global relationship, not about local balls or about balls as in the Chigurh-Rommel case, not about local Taylor expansions, but about the volume across of the fibers of the whole fibration. So once again, the positivity or negativity of Ricci is related to the convexity of the volume of those fibers. And what we have also shown in the G2 case is that from the analytic perspective, we can continue developing the Harvey-Lawson theory of plurisubharmonic functions by studying how they relate to submersions. And the analytic perspective provides a perfect analogy. But what we do not have in the current G2 situation is the extra ingredients of geometric positivity. We do not know how to define it. We do not know how to use it. And this is, I think, the type of framework in which it will be interesting to have that extra knowledge. So that's the end of the talk.
Yes, thank you very much, Tommaso, for your beautiful lecture.
Thank you.
Is there anybody has some questions? So I have one more question. Of course, I already asked you a lot during my your talk and interrupted you. But what I did on G2 geometry in the last year only. Also, I have the things that we can prove something for G2. We can prove for spin 7. Yeah. Mm. And then I don't know if you never think about the extension to spin 7 or.
Okay, so that's a good point. The fast answer is no, I did not. But I'm sure that the same, many of the same things will continue to work in a very similar way. The G2, some of the G2 formulae are a bit difficult to work with, like when you prove a second variation formula. They might be a little bit worse in the spin 7 case. But yes, I expect that there are some similar results, but you have to be careful. I think moduli spaces may be more difficult in the spin 7 case.
Yes, because, yeah.
I'm sure the function theory would work, yes, in some analogous way. So yes, it's certainly something that one could look at, and I think it would give results.
So that means you think that you can also define the concept subharmonic function for spin 7, or what is what do you expect that is more difficult, or that is not so so obvious?
So Harvey-Lawson have already given the definition of a plurisubharmonic function on a spin 7 manifold.
So I didn't notice, yeah.
Yes, yes. They have many papers which generalize classical pluripotential theory from complex analysis or Kähler geometry to all calibrated manifolds, and even beyond. They go beyond calibrated geometry. They talk about Grassmannian geometries, yes, and beyond that, other types of situations. So yes, the definitions, the function theory definitions are already there. But again, I think it's interesting that these have not been used by geometers yet. I think that is a place where it will be interesting to work.
So what is your next plan to assess geometric positivity or?
That would be nice. I don't know if it is not a short-term goal. I think it is unclear how to proceed, and it is unclear if it will actually work. I don't know. Maybe G2 geometry cannot be developed in that direction. I think it's an open question still. It would be, I think it's something that's worthwhile thinking about. But maybe it's a bad investment. I don't know.
Okay, if there are no more questions, let us thank the speaker again. Yeah.
Well, thanks to everybody for listening.
Yeah.
And,
thank you. It's a really beautiful lecture. Yeah.
Please contact me if you have questions.
So I can ask you for a slide.